Okay, so what we're going to do is we're going to go back to discussing a little bit of math. And so this will be based on, again, continuing in Nakahara chapter 5, where we left off. So since it's been a while since we reviewed this math, let's just recap exactly, some of the things that we learned. Okay, so we learned this broad idea of topological spaces, and if you remember what a topological space is, it's a set X along with a collection of sets U, okay, which satisfy certain properties, and these sets U are called open subsets, okay, of X. Okay, so these are subsets of X, and they satisfy certain properties, and that about their union and their intersection. And that allows you to define a topological space. And really, so essentially the idea of topology was about points and the neighborhoods of points. Okay, and then within topological spaces, there was a subclass which we were interested in, which are manifolds. Okay, and manifolds are topological spaces which locally have the topology of Rn. Okay, not globally, but local patches have the topology of Rn. And on manifolds, we were able to do calculus by defining things like differentiation, that is, by talking about curves, okay, or we can talk about tangent vectors to those curves, and that allows us to define the notion of a derivative. Okay, and so we would define vectors and differentiation, and then we generalize vectors to dual vectors and tensors as well. There's a notion of integration as well on manifolds, and that's something that maybe we'll discuss in some of the summer classes. Uh, Furthermore, we saw that on manifolds, you can also define a notion of parallel transport. That is, once you have a vector, how can I compare vectors at different points? Okay, and for that, we needed to define something called a connection, gamma, or equivalently, we need in a coordinate independent way, we defined this affine connection delta, which was this derivative operator, which allowed us to compare vectors at different points. And once you have a notion of a connection, okay, we saw that you can define things like torsion of this connection or the curvature of this connection. Okay, so this curvature is some additional structure that needs to be, sorry, this connection is some additional structure that needs to be imposed on a manifold. All right. And once you have such a connection, then you can also talk about geodesics, which are the straightest possible paths. That is, vectors along these paths. Okay, the tangent vectors V satisfy this equation in the affine parameterization. Del V is 0. Okay, so this was manifolds, and then within manifolds, if we impose even more additional structure, which is to say that there is a metric tensor, okay, a metric G mu nu, which is a type 0,2 tensor, okay, which is it has two dual vector type indices, and we assume some properties for these metrics, like its signature and so on. Then we saw that there is a unique connection gamma, which is metric compatible. Okay, that is, the metric does not change when I compare from point to point using this derivative operator. That is, this derivative operator preserves inner products of vectors. And this unique connection is metric compatible and it's torsion free. Okay, and if you demand these two conditions, you get this unique connection. And with this unique connection, you can calculate a curvature, and that curvature is called the Riemann curvature tensor. Okay, so this is a curvature which is associated with this connection, the unique metric compatible torsion free connection, which comes once you impose a metric on the manifold. And you also have more symmetry properties of this Riemann curvature tensor, okay, that satisfies these extra symmetries and also these Bianchi identities. And once you take this kind of connection, okay, the metric connection, then you get geodesics are not just straight lines, that is, the tangent vector doesn't just remain parallel to itself, but it also is the shortest or longest distance between any 2 points on the manifold. So it also extremizes the arc length. To even define a notion of distance, you needed to impose this metric. The metric allows you to talk about a distance along a curve, and that's how you can show that geodesics extremize the arc length. Okay, so this was the basic summary of all the mathematics that we essentially needed for GR. Okay, before you solve the Einstein equations, you just assume that you have a manifold. okay, and you solve for the metric on the manifold. Okay, that's essentially the essence of GR, is solving for that metric. Once you have the metric, particles which don't experience any forces other than gravitational move on geodesics. Okay, so this is the essence of GR. Now, what we'll do is we'll just go back to the basic manifolds. Okay, so very basic manifolds without the notion of this parallel transport or any connection. We'll just talk about manifolds, okay, where on which you can define differentiation vectors and tensors. Okay, so let's go back to basic manifolds without any kind of connection. So let's say that you have a manifold M, which is an n-dimensional manifold. And what does it mean to be a manifold? Well, it means that there are open sets U, okay, and there are mappings from these open sets into Rn, okay. And so once I have these mappings, essentially those are coordinates that I can assign to M, but those coordinates can be assigned locally, okay, not necessarily globally. And I have to patch together these coordinates to cover the entire space. So this is my manifold M. This is a point P. This red curve shows an open set U, okay, of this manifold. And this map psi U takes me from the point P to some point in Rn, okay, which has coordinates x mu of P. And this entire region U is mapped to an open subset of Rn. Okay, so that's sorry, an open set of Rn. Okay, so so that's the basic idea of how you assign coordinates to a manifold. Now we saw also how to define tangent vectors. So first we start by defining a curve. So we start with an open interval AB, okay, on which we parameterize where at some point T, okay, T lies in this open interval AB. And we use this to define a curve, okay, CT, as a map from this open interval to the manifold. Okay, so this is that curve. And this curve we assume passes through P. Okay. And now we can define the tangent vector at P by defining a map from the manifold to real numbers. So the entire manifold can be mapped to real numbers through some smooth function f. Okay, and so if I think about f circle psi inverse, okay, that is I start from this coordinate, I invert it to get the point P, and then I follow it by f to get a point on the real line. So this is a map from Rn, okay, to real numbers. And if this is a differentiable map, okay, then we say that this function f is c, that is at c infinity, infinitely differentiable. Then we say that this map f is a smooth function. Okay, so now we can define tangent vectors, okay, by this combination of this curve which passes through P and the mapping of the manifold to real numbers. So so the way we define the tangent vector is we defined an operation, okay, x acting on f. So given a function f, we define an operation x acting on f as the rate of change of f, that is df by dt. So as I move along the curve, okay, as I move along the curve, we want df by dt, and we assume at t is equal to 0 is the special point where we pass through P. Okay, that's without loss of generality. So x of f was defined as df by dt, where I'm evaluating it on this curve c of t at t is equal to 0. And we saw that this can be written as partial f partial x mu, okay, by the chain rule. F depends on where I am, okay, which is on the coordinates x mu of t. So I can differentiate with respect to the coordinates x mu, and therefore each coordinate can be differentiated with respect to t. And this is a summation over mu, which is implicit. Okay. Sorry, is there a bit of a lag? You're not seeing the, are you not seeing the summation sign?
Sir, it's visible.
Yeah. Did the summation sign come on when I first said it, or did it come on, after I said asked if there's a lag?
There was a slight lag, but I think it's fine.
Okay, just let me know if the lag gets too much, and then I'll try to reconnect my iPad. Okay. So this was at t is equal to 0. So this has to be evaluated at t is equal to 0. This defines the operation x of f, okay, at the point P. So so this is x of f, where this x of f is defined at the point P. So now we can define for any function f, okay, you can define this operation x as x mu partial partial x mu, where these components x mu are dx mu dt. Okay, so this operation defines a vector. Okay, it is a vector at P. Okay, so this is what we call the tangent vector at the point P. Okay, so this was a way in which we are allowed to define tangent vectors on arbitrary manifolds through an operation. Okay, now what we saw is that if we take all curves through P, or some equivalence class of curves through P, then by taking different curves, we get different tangent vectors, and this allows us to define a tangent vector space at P. Okay, and this was called TP of M. And then we generalize this to dual vectors. So we got dual vectors TP star of M at P. So we defined a dual vector W, or let's say omega, belonging to this dual vector space. And if we have a vector V belonging to the vector space TP of M, then we defined an inner product between the dual vectors and vectors, and saying that that belongs to real numbers. Okay, and so it allowed us to define dual vectors, and then it also allowed us to define tensors. So tensors, so these kind of mixed tensors where you have Q indices which are vector-like and R indices which are dual vector-like at every point P on the manifold. And if you assume that the vector fields or tensor fields are smooth over the entire manifold, you get smooth tensor fields, which are basically defined at every point on the manifold. So you don't need to specify this point P. So this is the space of all tensors of type QR on the manifold M. Okay, these are smooth tensor fields on the manifold. So hopefully all this is familiar. It's just been a while since we've seen this, right? So it's just good as a refresher to remember these arguments. Okay, anything that you don't remember or you want to ask again, that's perfectly fine. We can have the discussion now. Okay, so now we come to the new thing that we're going to do. Okay, so the first thing we're going to talk about are what are called induced maps. Okay, so let me explain the setup. So let's imagine that we have two manifolds. Okay, so we have a manifold M, which is dimension small m, and a manifold N, which is dimension small n. Okay, M and N are arbitrary size. Okay, so one can be larger, one can be smaller. And so what it means is capital M is locally isomorphic to Rm. Okay, and capital N is locally isomorphic to Rn. And now let's imagine that we have a smooth map between M and N. Okay, so what does that mean? So this is the manifold M. This is a point P on the manifold M, and this red shows this red boundary shows an open subset of M. And so these points on this open subset have coordinates which we denote as x mu of P. Okay, and there is a function f which maps every point P on this manifold M to some point f of P in this manifold N. Okay, shown in magenta. And now we'll assume that we're working in some particular open subset in N. Okay, so in this open subset, this point f of P has coordinates which are denoted as y nu of f of P. Okay, so this mu index runs from 1 through m because capital M is an m-dimensional manifold, so it must have m coordinates which are needed to represent each point. Similarly, capital N is n-dimensional, so this y nu runs from 1 through n because there are n indices, okay, needed to represent a particular point. And smoothness of this map f just means that these functions y nu as a function of these x mu's, okay, these are C infinity functions. Okay, and this is true for every coordinate chart that you can impose on M and N. Okay, okay. So now this point P has a tangent space, which is the tangent space at P on M. Okay, and this is an m-dimensional vector space. Okay, because there are m independent tangent vectors that you can construct at P. This point f of P has a tangent space Tf of P of M, and this is an n-dimensional vector space. Okay, and P also has a dual vector space, which is Tp star M, which is also m-dimensional, and f of P has a dual vector space T star f of P of M, which is also n-dimensional. Okay, so this is the basic setup, and now I'll make a claim. And the claim is that this smooth map F, okay, between the manifolds M and N, what it does is it induces two maps for every point P belonging to M. Okay, so given a point P belonging to M, I'm now going to get two more maps. Okay, and the first map is called the differential map. It's a map from the tangent vector space at P to the tangent vector space at F of P. Okay, these are two different vector spaces. Okay, one is a vector space TP of M, which is M dimensional. The other is a vector space on F of P, which is N dimensional. Okay, so the claim is that this F induces a map. So that means given a vector here, I can map it to a particular vector in this dual vector in the vector space on this point in N. Okay, so the claim is that there is a map between the vector spaces. Okay, between a vector in this space to a vector in this space. It takes me from a vector in this space to a vector in that space. Okay, so this map is called F lower star. Okay, it's a map from vectors on M at the point P to vectors on N at the point F of P. Okay, so the claim is that this map exists and it's called a differential map. And the second claim is that there exists something called a pullback map. Okay, and this pullback map is a map from dual vectors. Okay, that is, I construct a dual vector here, which is something belonging to T F of P star at M. And given a dual vector here on N, it maps me to a dual vector at the point P. Okay, that is, I get something in TP star of N. So it's called a pullback because the map goes in the opposite direction. Okay, it goes from N, the dual vectors in N, to a dual vector in M at the point P. Okay, so this is called the pullback map. F, and this is denoted with F upper star, T star F of P on N. Okay, that is the dual vector tangent space at F of P. Each dual vector there can be mapped to a dual vector at the point P. Okay, so in other words, what we're saying is that there are two maps which are induced by the smooth function F, which takes us from M to N. It's a mapping of vectors. Okay, but the mapping is such that the mapping is uniquely defined as a forward mapping for vectors. That is, it takes vectors in the tangent space of P, brings it forward to a vector in the tangent space of F of P. But it's a reverse mapping or a pullback for dual vectors in the dual vector space on at the point F of P. It brings them back to a dual vector on at the point P. Okay, and you might guess the obvious thing, which is there is no forward map for dual vectors, and there is no backward map that is naturally defined for vectors. Okay, so so we'll see why this is, and we'll see under what conditions that the reverse maps are also defined. Okay, any questions about this? Is this basic idea clear?
Yes, so just one small clarification. So far we haven't assumed anything about the dimensions of n or m, right? So
just that M is M dimensional and N is N dimensional. That's all.
Yeah,
but
so
there's no specification.
yeah, so either smaller or larger, and the differential and pullback vectors would mapping would still be defined.
They would still exist, yes. No matter what the dimensions, whether M is greater than N or M is less than N.
So it seems rather strange to state. I mean, you said you're going to describe it, but it seems rather strange to say that the differential map makes sense only from M to N or N to M. So
yeah, we'll see why that is. Okay, we'll construct it and we'll understand why this is. Okay, so what we're going to do next is we're going to construct these maps, the differential map and the pullback map explicitly, okay, to see what that mapping is. Okay, so that's what we'll do next. Okay, so that's what I've written here. Let us explicitly construct the maps. That is, we'll construct this differential map from TP of M to TF of P of N, and we'll construct this other map F star, the pullback map from the dual vector space at F of P to the dual vector space at P. Okay, so so here's the idea. Okay, so again, to define vectors, we had to think about curves. Okay, so let's think about curves. So this is the manifold M. Okay, there's a mapping from a point P through this function F to a point F of P on N. Now, what we do is let's think of a curve which passes through P. Okay, so what do we mean by a curve that passes through P? It means that we start with an open interval AB. We define a curve C of T such that at T is equal to 0, this curve passes through the point P. So the C of T is a map from this open interval AB to the manifold M. And so it gives me some curve. And we'll assume that at T is equal to 0, that curve passes through P. Okay, and the coordinates of different points here we'll denote as x mu, and let's say of the point P in particular is x mu of P. And this curve, okay, will also, because of F, all the points on this curve get mapped to a curve in N. Okay, so I can, so the curve C of T, of course, defines a curve on M, but through F, it also defines a curve on N. Okay, so this is, it's easy to understand what it is. It's F circle C of T. Okay, so I apply F to every point on this curve, and that brings me forward to some point here. And obviously F acting on C of 0, which is P, will bring me to F of P. Okay, it'll bring me to this point. And now we assume that again, since this point F of P has some coordinates y nu, okay, and this y nu for F of P. Okay, and now we'll assume the existence of some function g. Okay, this is a smooth function on the manifold n. So it's a smooth function that takes us from n to real numbers. Okay, so there's some smooth function g which takes us from n to real numbers. Okay, so the function g is a smooth map from n to r. Okay, but now here's the interesting thing. Okay, through this function f, okay, through this function f, this smooth function g also defines a smooth function from m to real numbers. Okay, so for every point on m, this function f will take me to a point on n, and this point on n through g will take me to a point on r. Okay, and since f and g are both smooth, G circle F will also be smooth, and G circle F is a map from points on M. Okay, first I act with F, it takes me to some point in N, then I act with G, it takes me to some point in R. So that is G circle F. So G circle F is a smooth function on M. Okay, so what this means is that we can directly think about the function G circle F, which takes us here. Okay, so it's like we start with a curve on M. And these curves on M, okay, we can define functions on them, okay, which are induced by via G and F. Okay, so given a G, I can get a G circle F, which takes me from M to points on real numbers. Okay, and also given a curve on M, we can also get a curve through N. Okay, so we get these two extra things through this this map between the manifolds F between M and N. Okay, so given a manifold M, okay, so now let's start with this. So given a manifold M with a curve through P and this function G circle F. So we have a curve, which is defined from here. We have this function G circle F. So now given a function, given a curve, we can define a derivative operator at P. Okay, as we did before. So is a derivative operator x of P acting on this function G circle F. And it's nothing but d of this function G circle F dt. Okay, so instead of df dt, f is not a function which takes me to real numbers. F is a function which takes me to n. So I don't define differentiation with respect of f. I define rather differentiation of G circle F, because G circle F takes me from m to real numbers. Okay, so now we can define this differentiation. Okay, and we define it at t is equal to 0. Okay, that gives me a vector at the point P. So this is partial x mu of G circle F dx mu dt at the point P. So this allows me to define tangent vectors xp, which are dx mu dt partial x mu at P. Okay, so these tangent vectors are independent of the choice of G. Okay, so given a G, I now have a way to construct such a tangent vector. Okay, if you give me G, I will first use my map F. Okay, so G is a map from N to R. I will use my map F to construct this function G circle F from M to R. And now I use that to define a tangent vector on at the point P. Okay, so this is the first thing that we've done is now we've constructed a tangent vector at the point P. Okay, so we constructed this tangent vector at the point P. Now what we're going to do is we're going to construct a corresponding tangent vector at the point F of P. Okay, we're going to construct a corresponding tangent vector at the point F of P. So what is this corresponding tangent vector at the point F of P? Well, on N, okay, we can define a tangent vector because now we have a curve on N. Okay, how did this curve get created? Well, once we created a curve on M, F induces a curve on N. Okay, so this curve gets mapped to a curve on N. And once we have a curve on N, this gives us a direction along which we can differentiate. And so this function G can be differentiated along this curve. Okay, so we can define a derivative or a vector through an operation y. So this y is defined at the point F of P. Okay, so y of f of P acting on G is equal to dg by dt. Okay, again, this is at t is equal to 0. T is equal to 0 maps me to P, and through F it maps me to f of P. Okay, so so this defines an operation. Okay, this defines an operation on G, and that operation is take dg by dt at t is equal to 0. Okay, and really what we're doing by the chain rule, okay, this operation y is taking dy by dt, okay, of partial y nu at the point f of P. Okay, so this operation y now does not depend on G. Okay, so this operation y, given any G, I can differentiate it, okay, along this curve. So this is independent of the choice of G. So this gives me a vector. Okay, but these dy by dt, okay, is an induced map. Okay, this curve is induced by the fact that I had a curve in M and then I used F to get a curve on N. Okay, so we can write this explicitly, this induction of this curve. So dy by dt is really a map. Okay, so this is really, you should think of y is points in N, okay, along this curve. Okay, so these points in y are really functions of x mu of t. Okay, so what that is, when I take points along the curve in M, okay, and then I take the corresponding coordinates of those points in N. Okay, so this is sort of using F, okay, which is the mapping from X to Y, and this is C of t. Okay, that's the original curve in M. So what we can do is we can apply the chain rule. So dy by dt can be written as partial y nu partial x mu dx mu dt. Okay, partial y nu. Okay, again evaluated at the point f of P. So these dx mu by dt, these are nothing but the coefficients x mu, okay, of this vector, okay, the vector that we defined at the point P. So this is x mu times partial y nu partial x mu, okay, from here, times partial y nu at f of P. Okay, so these are the components of the vector y. Okay, so these are the components of the vector y, which I can write as some y nu partial y nu. Okay, so these are the components. So now I've explicitly constructed this map. Okay, so I've constructed f star, which takes me from a vector x. Okay, this x is defined at P. Yeah, so if I have a vector x at P, it takes me to a vector y defined at f of P. In components, what is this map? Well, it's telling me y nu is equal to x mu partial y nu partial x mu. Okay, but it's easy to understand what we have done, right? We differentiated G circle F along this curve, or equivalently, we differentiate G along this curve. Okay, this defines a vector X in M, and this differentiation defines a vector Y in N. Okay, so all we've done is just get the mapping from this X to this Y. Okay, and the key point of all of this is you were allowed to define by composing G and F, you can construct G circle F, which is a map from M directly to real numbers. Okay, and you are also allowed to construct a curve directly in N by composing C of T with F. Okay, that gives you this curve. So the fact that you can perform these two operations, okay, is what leads to the mapping between X and Y. Okay, and in components, it's this. Okay, and so note that these are different vector spaces. Okay, this y nu is defined in the vector space on f of p. Okay, which is in N. So this vector space is n dimensional. Okay, this is an n dimensional vector space, and these are the components of that n dimensional vector. Whereas this x mu, okay, lives in an m dimensional vector space, which is the vector space at p in M. Okay, and the transformation to get from this m dimensional vector space to this n dimensional vector space, okay, is partial y nu partial x mu, which is the Jacobian, nothing but the Jacobian of the transformation of f from M to N. Okay, so in components, what does this look like? Well, if I write this x mu as some x0, x1, dot, 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 till x small m. Okay, I have a non-square matrix in general. Okay, with m columns and n rows. And the entries of this matrix are partial y nu partial x mu. Okay, where mu denotes the column and nu denotes the row. Okay, and the output of this is an n-dimensional column vector y0, y1, y2 to yn. Okay, so this is nothing but the Jacobian of the transformation. It's a non-square Jacobian because the transformation is from m variables to n variables. Okay, and this is basically the transformation rule for the vectors. And so the vectors are not trivially mapped; they're non-trivially mapped. The non-trivial mapping is because you are using a Jacobian for this transformation. And in general, these are vectors in different dimensional vector spaces. Okay, is this clear? Any questions here?
So here capital 1, capital X are just any two vectors in eminent, right?
Sorry, say that again.
Capital X and capital Y are any two vectors in eminent.
No, they're related, right? These are not arbitrary vectors. So one given an X, I can tell you what the Y is.
Yeah.
Okay, but the reverse is not true. Given an arbitrary Y, I cannot construct an X for it.
Right, got it.
Right. So the reason being, right, I mean, it's easy to understand why. Right now, if I give you an arbitrary vector here, okay, that arbitrary vector here, I would have to define a curve, okay, along which I'm differentiating it. But I don't have the freedom to define that curve in N. Okay, the curve is defined on M and F induces the curve on N. Okay, so it may be that f is such that it doesn't allow certain curves on M to be mapped to arbitrary curves in N. Like you might only get a subset of the curves on N. Okay, so that is why you can't really define, you can't, given a y, you can't always get an x for it. Okay, but given an x, you can always get a y for it.
So that's basically equivalent to saying that you can't go from a high, like have a map from a lower dimensional vector space to a higher one, right? Like it's like projecting a vector from a 3-dimensional vector space to a 2-dimensional vector space, but you can't define an inverse for that map because you're losing information.
No, that's not what's happening here. I mean, M can have dimensions which are less than N. It can be more than N. Both are possible.
I see. Okay. Okay.
Sir, just to confirm that I understood the argument correctly. So the first step is just we define the tangent vector on M using GOF. And then we have the mapping using f from m to n, and then we have fp, and that operating on the function g will give us y mu. But how did you relate y mu to x nu?
Sorry, so YFP on G, okay, I said is the same as XP on G circular.
Because it maps to the same real number.
This gives me the same real number, yes. And this mapping is basically independent of the choice of G. Okay, so that basically gives, I mean, so basically this defines, this is not a vector, this is a real number, right? But this is the action of a vector in N on G. And this is the action of a vector in M, sorry, in the tangent space TPM, really, okay, on G circle F. Now, this relationship is true for any function G that I choose. Okay, and so these vectors, okay, are mapped to these vectors. Sorry, so given, sorry, let me reverse that argument. So given XP, okay, I can get Y of F of P.
Yes, sir. Now I think I get it. So because y fp of g, which is a real number, and is the same real number as xp applying on g of f, and since this works for any arbitrary function g, so it must be that the vectors are related, and then we have the expression with the Jacobian.
Right. Yeah, and the reason why it doesn't work in reverse is that you're defining the curves on M. Okay, so that means you can construct any arbitrary XP by choosing arbitrary curves on M. Okay, but these arbitrary curves on M may not give you all possible curves through this point f of p on N. Okay, it depends on what this map f is. Okay, so if it doesn't give you all possible curves, then you're not going to get all possible tangent vectors.
Yes, it makes sense. So, but instead, if f were a bijective function, then I think we could do it backwards. Then the Jacobian, then we could have constructed the relation between y and then back to x if f were an invertible function.
Yeah, excellent. That's a very good point, and we'll discuss that later. So if this mapping has an inverse, which is to say that this is a diffeomorphism. Okay, if it's a diffeomorphism, that means that this manifold M has to have the same dimension as the manifold N. Okay, for the inverse to exist. So this is a diffeomorphism. If the diffeomorphism exists, then this inverse mapping also exists. Okay, so that is if F is bijective or this is diffeomorphic map. So then is asking, wouldn't it be more appropriate to write G circle F circle C instead of G circle F? No, so when I'm saying P, so P is already C. So I'm evaluating this at a point on X. Okay, and this X is defined through the point P. Okay, so P is already giving me the point on the curve that I'm at. So, I mean, yes, there is some abuse of notation in the sense that, strictly speaking, you have to be careful whether, I mean, I'm not really making being careful to distinguish the coordinate from the point P. Okay. But I'm not sure if that's what you were asking at the end.
I think the P makes it clear because if you just write X, it's usually acting on something from R to R. So that is why I was confused.
Yeah, the subscript P is telling you that it's specifically at the point P.
Yeah.
Okay, so at the moment, okay, so you also see why. So if I only have a forward map from M to N, there's no inverse map. Okay, then you only given an X of X at the point P, that gives me a Y in F of P, but the reverse statement is not true. Okay, given an arbitrary vector on at the point F of P, I can't construct a vector that corresponds to, I can't necessarily construct a vector that corresponds to it in M. Okay, so this now, so what you can do, but is this map can be extended to tensors which are all where all the indices are of vector type. Okay, so everything which is of vector type index. Okay, so Q0 at the point P, I can define the components of a Q-dimensional vector, sorry, Q-dimensional tensor, a type Q0 tensor. Okay, on N, okay, on F of P. Okay, so these are the components of this, and these are the components on tau Q0 at P. Okay, this is on M. And this is the transformation. Okay, so it's a Jacobian applied to every index. Okay, so it's possible to push forward vectors. Okay, or tensor products or tensors constructed with all vector indices. Okay, you can push those forward. Okay, but you can't pull them back. You can't pull back vectors from N to M. You can only push forward vectors from M to N. Okay, so here's a simple homework exercise, which is kind of easy to convince yourself already is true. So if I have a map from M to N, okay, so if I have three manifolds, M, N, P, okay, so a map F from M to N and a map G from N to P, then this push forward map, okay, which is, so if I take the map from M to P, that map is G circle F. Okay, so now if I want to construct a vector, so given a vector at the point P in M, if I want to construct the corresponding, so this is G circle F of P. Okay, that's the point in capital P. And if I want to construct a corresponding vector to this, okay, the map which takes me from this to this is called G circle F star. Okay, so given this function with a lower star, that is the push forward map, okay, or the differential map. So it's quite easy to convince yourself that this push forward map is first the map that takes me from here to here, which is F star, followed by, so it takes me to a vector here, and then given a vector here, it takes me to a vector here. This is G star. So it's G star circle F star. Okay. Sorry, that's not really a homework exercise. I mean, this is the proof. Okay. So G circle F star, this composite push forward is G star circle F star. Okay. Now what we'll do is we'll construct the pullback map. Okay, so we saw that vectors can be pushed forward. Okay, but now we'll see that dual vectors can only be pulled back. They can't be pushed forward. Okay, so if I take f star, okay, from f star is defined as a map from the dual vector space at f of p, okay, which is in the dual vector space at n, to the dual vector space at p, okay, in M. So how do we see this? Well, it's actually easy to construct from the push forward map. So suppose we have a dual vector omega, okay, which belongs to this space. Okay, that is the dual vector space at the point in N. Now what we do is we construct the pullback. Okay, so given in f star, so given in this function f star omega will give us something in the dual vector space on M. Okay, so in pictorially this is M, this is N. So of course I can push forward vectors. So given a vector v, I can get given a vector x, I can get a vector y. Now we're saying given a dual vector here, okay, any arbitrary dual vector, I can always get a corresponding dual vector in this space, okay, at P. And this dual vector is denoted as f star of omega, the pullback of omega. Okay, and the way we define it is by using the inner products between dual vectors and vectors. Okay, so what we do is we say that if I have a vector x whose push forward is y, okay, or instead of y, I can write the push forward as f star, f lower star of x. Okay, so f lower star, remember, is the push forward map or the differential map. And this f upper star is the pullback map, which acts on dual vectors. Okay, and f star acts on vectors. So x gets mapped to f star of x. Okay, and omega we're claiming gets mapped to f star of omega. So we now need to define what we mean by this map f star omega. So we define the map f star omega such that it preserves the inner product between these two vectors. So this vector and this dual vector, that is y and omega, or equivalently f star x and omega. Okay, so this quantity here, I denoted it as v, but we could write it as x, f star x and omega. This is an inner product which is defined on the manifold n. Okay, or in other words, it's defined at f of p. We say that this inner product is equal to the inner product between f star omega and x. Okay, this is going to define what we mean by f star omega. Okay, this inner product mapping should be true for any x. Okay, so this is x again. So for any x, it should be true that this inner product satisfies this property. Okay, that is going to define what we mean by f star omega. Okay, so let's see in coordinates what this works out to be. So suppose that this dual vector f star omega, which is a dual vector at P, can be written in components as psi mu dx mu. Okay, so remember the components here, coordinates are x mu. So the basis of dual vectors is dx mu. Okay, so we write the basis dual vector coefficients as xi mu dx mu. Okay, then this inner product, I can write as, I'm going to write x mu as, so I'm going to write this I'm going to write this dual vector x, okay, as some v mu prime partial x mu prime. So the prime is just a dummy index, so don't worry about the prime. Okay, this v mu prime is, I was using v before, so I'm just going to leave it as v. Okay, so these are the components of this vector. So the left hand side is this inner product. Okay, and this inner product, we know what it is, right? It takes dx mu, and only when this mu index matches this mu prime index, okay, it's non-zero. So what we're going to get is xi mu v mu, where there's only one index now, which is summed. Okay, that's the inner product, and that's the usual way we're used to writing this inner product. Okay, and this is really the components of f star omega. The xi's are the components of f star omega. And on the right hand side, okay, we have this inner product which is not evaluated at P, but rather on f of P, which is over here. Okay, which is omega f star x. So let's write what that is. That is omega nu dx nu. And now we have this push forward of v. So f star v with some coordinate nu prime. Okay, partial y nu prime. Y because the coordinates are Y over here. So this Y news. And we have the push forward of the vector V. Okay, the vector V was, or the vector X was defined at this point here, which was on P. And we have a formula. Okay, so sorry. And again, we can take this dot product easily. It's omega nu F star V, okay, the new index. And we know what these components of the push forward of this vector are, right? We just worked it out. It's the Jacobian times V mu. Okay, so it's partial Y nu, partial X mu, V mu. Okay, so this is the right hand side. So now if we equate these two, okay, these inner products should match for any V mu, okay, or for any vector V, which means we can equate the coefficients of V mu. And what we get is xi mu is equal to omega nu partial Y nu partial X mu. Okay, so in other words, so we have an m-dimensional vector here, we have an m-dimensional vector here, and we have an n-dimensional an n-dimensional vector here. So how do we think of this? Well, if we think about our same Jacobian matrix, okay, our previously the way we had written the Jacobian matrix was we had written it as m columns and n rows. Okay, so we'll keep that notation. So m columns and n rows. And now this omega nu we think of as a row vector. Okay, this row vector is n entries. This is omega nu. Okay, this is the Jacobian. And this is equal to the row vector xi mu. Okay, which has m entries. Okay, so this is the map from a dual vector where this dual vector is on P star Fp of n. Okay, and it maps me to a dual vector which is now on M, on capital M, Tp star of n. Okay, so the fact that vectors can only be pushed forward automatically gives you that dual vectors can only be pushed backwards. Okay, so that is, so given a V and a forward push forward, okay, I take a dual vector omega, okay, which has some particular inner product with this, and I correspondingly ask for the dual vector in this tangent space, this dual vector space. Okay, such this is a dual vector in this tangent space, and I ask for it in such a way that this gives me the same inner product with this V. Okay, and I demand that this is true for any V. So basically what I'm going to do is now given a dual vector, this is an arbitrary dual vector on n at the point f of p, it gives me a dual vector at the point p in m. Okay, so vectors get pushed forward, dual vectors get pushed back. Okay, and this can be generalized to any tensor which has only dual vector type indices. So dual vector type indices being, let's say 0 r, okay, at the point p of m. So so this is a dual vector at f of p, okay, on n, and this is the components of a dual vector at p on m. Okay, and they're related by again r Jacobian factors. Okay, any questions about this?
Sir,
Yeah.
When you are writing omega as omega nu dx nu, shouldn't that be omega nu dy nu?
Omega, omega, where did I write omega? Yes, thank you. This one. Yes, very good point. Because the dual vectors are dy nu. Thanks. Yeah, and indeed dy nu with partial y nu prime, right? That is the thing that is delta nu prime. So the rest of the argument still works. I just use the wrong coordinate here. Okay, because the coordinates y are the coordinates on n by assumption.
We could have done the same thing in a reverse manner, right? I would define a dual vector in M, and we say that the push forward for that has to be such that the inner product once again is preserved.
Okay, so let's try that. Okay. So let's take M. Okay, let's take the point P, and let's take an arbitrary vector V, and let's take an arbitrary dual vector omega. Okay. And now let's take N. Let's take the point F of P. Let's take the push forward of V, which is F star V. And now let's suppose that there exists a map. Okay, we'll call this map a hypothetical map H. Okay, H upper star. Okay, which maps us to a dual vector in N. Okay, and we demand that for arbitrary V, okay, omega V should match H star omega F star V. Okay. See the problem with this is roughly the same as before. F star V doesn't give me all possible vectors on N. Okay, so if I'm using this to define the map H star, okay, I want to be able to I don't have the freedom to choose this inner product, okay, in such a way that this can be arranged for every V. Okay, because what I need is that this should be this right. So this is only a subset, okay, of all possible vectors T, F, P, N.
Yeah, so I understand it's a subset. I don't see the problem with it being a subset because even if we just had one vector, we can still define inner product with it, right? It still lies in the same space. It lies in the vector space at P, and the dual vector lies in the dual vector space at P. So we can still define inner products.
The inner product can be defined. The point is that you want a mapping, right? So this H star omega should be uniquely defined, and this relationship should be satisfied for arbitrary V. Okay, so let's write it in components. Okay, so we'll see what the problem is. So we'll write omega mu V mu is equal to H star omega. Sorry, the other way. H star omega nu, and this F star V is we can write it in using the Jacobian partial y nu partial x mu v mu. Okay, this relationship should be satisfied for arbitrary v mu. Okay, which means this should be true. Okay, and this Jacobian in general is non-invertible unless the map is invertible between y and x.
Okay.
Yeah, this is sort of coordinate dependent. I mean, okay, just having trouble articulating exactly why in a coordinate independent way you can see this, but it's essentially the same reason as that we're seeing in the coordinate dependent way. But so sort of here, okay, in this proof, the definition, right, of this, we don't have to invert anything, right, when we're saying that this is true for arbitrary x.
Yeah, okay. I know. I got confused. I thought we could add 1 by, but I forgot it's a summation and all that. So
Yeah. Yeah, it is not well, even if it's a square matrix, if it's not an invertible square matrix, that is
yeah.
that can happen. Jacobian is non-zero, right? Then you can't invert it.
Okay. Got it. Thank you.
Okay. All right. So summary. Okay. So vectors can be pushed forward in general. Dual vectors can only be pushed back in general. Okay. So now if we have general choices of the manifolds M, N, and F, as we've assumed before, then the first thing is there's no generalization of these induced maps for mixed tensors. Okay. And in particular, that means that there's no natural map from dual vectors cannot be pushed forward. Okay. That is, dual vectors in M cannot be taken to arbitrary dual vectors in N at this point f of p. And similarly, vectors in N cannot be naturally mapped to vectors in M. Okay, F doesn't naturally induce such a map. The exception to these rules, as asked earlier and pointed out by Kaustav, is when the map F is invertible. Okay, that is, if there's a map from M to N, but that also gives you an inverse map, F inverse, then the map from M to N is a diffeomorphism. Okay, so this map is a diffeomorphism. There's a one-to-one map between M and N. In that case, okay, so if F from M to N is defined and F inverse from N to N is defined, then it is actually possible to also do the reverse. Okay, to do the reverse thing, which is to push forward dual vectors and to pull back vectors. Okay, so you can do the reverse operation, which was previously forbidden. Okay, and in a coordinate dependent way, the Jacobian becomes invertible. Okay, so so it's easy to see how you'd construct these maps. Okay, so if I have a map from M to N, we've already constructed the differential map and the pullback map. So this differential map takes me from TPM to TFPFN, and F star takes me from TFP star N to TP star M. Okay, these can be constructed. But now if I have the inverse map, F inverse, okay, then I can just repeat the same arguments and construct F inverse star. Okay, where now my starting manifold is N and my ending manifold is M. So I can just replace M by N here and N by M here. Okay, so given some, so rather let me say there's a point Q on N. Okay, and now I can construct a point F inverse Q on M. Okay, so this map exists. Okay, and also given a point F inverse Q, I can, so if I call this point P, then I can uniquely find through F, okay, its image in N. Okay, so that's why I had previously written this as this is in the tangent space TP of M, and this is in the tangent space of F of P. Okay, so this is basically allowing me to construct that. It's allowing me to take a vector in N and pull it back to a vector in M. So this previously forbidden operation of the pullback of vectors, okay, now becomes allowed if you have a diffeomorphism. And similarly, you can also push forward dual vectors. Okay, so if I have a dual vector at P in M, I can now push it forward using this F inverse star. Okay, sorry, F inverse, I think upper star. Okay, the upper star is the pullback map. Okay, so this pullback map, okay, I now define as a sort of, I can think of it as a push forward map, okay, of dual vectors. Okay, this is a pullback map if I think about F inverse, okay, because it's F inverse acts this way and I'm pulling back a dual vector from here to here. Okay, but I can now think of this as a push forward of a dual vector if I think about the map F from M to N. Okay, and so in components, okay, we can write down, for example, these quantities. So if I take the original F star from TPM to TFPFN, okay, that, so if I have this with components in TFP of N, omega nu, that is the original vector times this Jacobian. And now this F inverse star, okay, I can do the same thing. So I can now think about xi nu is equal to omega mu partial x mu partial y mu. So this relies on the inverse Jacobian. Okay, because I was using the inverse map F inverse here. Okay, so provided the inverse Jacobian exists, and we're assuming it exists in every coordinate patch if you have a diffeomorphism, then this mapping will always work. Okay, so you can have push forward and pull back of vectors and dual vectors. Okay, but the important point is that is only valid if you have a diffeomorphism. If it's not a diffeomorphism, you can only push forward vectors and you can only pull back dual vectors. Okay, so now let me just construct an explicit example. So supposing we have a diffeomorphism between M and N. Okay, then if I have a tangent vector T, okay, which belongs to which is of type 1, 1. Okay, so it's one vector index, one dual vector index at P. Okay, this induces a dual vector T prime in N. Okay, which is tau 1, 1 F of P of M. And this T prime mu nu, okay, the components of the tensor here with one vector index, one dual vector index, are related to the components of the tensor here with one vector index with at one dual vector index through a Jacobian and one inverse Jacobian. Okay, because I insisted on pushing forward both indices. Okay, and so if I pushed forward both the indices, the only way I can do that is the vectors obviously can be pushed forward. Okay, the dual vector can also be the dual vector type index can also be pushed forward if I have a diffeomorphism, that is if the inverse Jacobian exists. Okay, so so now this seems sort of ad hoc, like, you know, why did we talk about this push forward and pull back? But we'll see that when we talk about these ideas of Lie derivatives, okay, and Lie derivatives, if you remember in GR, why they're important is because the Lie bracket or which are related to Lie derivatives is gives you the symmetries or the isometries or uh, sorry, the algebra of the killing vectors. Okay, so if I have killing vectors k1, k2, two different killing vector fields, this k1, k2 at any point will be related to some other killing vector. Okay, so this and this can be written as the Lie derivative of k2 along k1. Okay, so this algebra of killing vectors is related to Lie derivatives. Okay, and this algebra of killing vectors is related to the symmetries or what we call the isometries of the metric. So in the Schwarzschild case, we wanted to understand, you know, there's this SO3 algebra, and that allows us to define the manifold or the solution to Einstein's equations in a way that is coordinate independent. Okay, so we're looking for solutions with some kind of spherical symmetry. And so to construct that, you need to talk about Lie derivatives, which we're going to do in the next class, but we'll need some of these results when we're talking about Lie derivatives. Okay, so that's just to give you context of when this will be useful. Okay, let's see. Okay, maybe we'll stop here and we'll continue next time. Okay, so we'll stop here. Next class we'll do on Monday next week at the same time, Monday at 4 p.m. Okay, any questions? Any last minute questions? Otherwise, we'll stop. Okay, if not, see you next week then. Bye.